welcome to today's class. We are discussing the solar system, and in the last class I told you that we have these planets in the solar system, 8 planets, and there are a few corrections to what I had told you. So, let me just go through those first. So, yeah. So, the first thing that I should point out is that the value of A over here, the value over here which I had shown you this table in the last class, the values over here refer to the semi major axis. Okay, it was mistakenly written major axis in the last class. This is the semi major axis of the elliptical orbit in which the planets move. Okay. The second point is that some of the entries in this table were incorrect, and this shows you the correct entries. The point to note over here is not in this one, sorry, in the next one. Some of the entries here were incorrect, and the point to note is that the outer planets rotate quite rapidly. Their orbital period, their rotation periods are pretty small. Okay. The values were incorrectly typed in the last class. The third point, this was a question raised by one of you. It refers to this rotation, and the question asked was, with reference to which plane or which axis is this angle of the rotation axis given? Well, it is given, the rotation axis angle is given, shown here, with respect to the plane of the revolution. So, for each planet it has a elliptical orbit and it has a plane in which the of the ellipse. So, the rotation axis shown over here is the planet's rotation axis, the angle that it makes to the normal to the plane in which it revolves. Okay. So, let me briefly summarize what we had learnt in the last class. We have these 8 planets and they all revolve in elliptical orbits around the Sun. The inner planets are rocky up to Mars, they are all rocky, and they are quite small, relatively small. The outer planets, the inner planets are pretty rocky. So, this shows you the inner solar system, and the outer planets, they are quite big, few thousand times at least the mass of the earth, and they are largely gaseous, the Jovian planets. Okay. So, that is a brief summary. Now, we also discussed what happened to Pluto, why it is no longer considered a planet, but it is now considered as a dwarf planet. And I told you that there are other dwarf planets also besides Pluto, and I told you that about 2 more dwarf planets. These are Ceres and Eris, and we shall come back to these dwarf planets again in today's class. So, having discussed the planets which are and the Sun is the most dominant component of the solar system, and after that we have the planets which are the second most dominant components. Let me now go on to asteroids, which are again another component of the solar system. So, what are asteroids? Asteroids are small bodies, these are small objects, rocky bodies in orbit around the Sun. Okay. So, they are mainly made up of rocks and metals, asteroids, and they are in orbit around the Sun, and the sizes of these asteroids could vary from 1 kilometer to a few hundred, say 948 kilometers for Ceres, which we have seen is now classified. It could vary from a few meters, okay, to 900, around 1000 kilometers, which is the size of Ceres, which now we have seen is classified as a dwarf planet. Okay. So, they could vary in size from a few meters to very large, few thousand, of the order of 1000 kilometers. Okay. And they are primarily in orbit between Jupiter and Mars. So, between Mars and Jupiter, if you look at it, if you go to the orbital distances, semi-major axis, Mars, the semi-major axis, they are roughly circular orbits. So, you can think of it as the radius is 1.5 astronomical units, whereas for Jupiter it is 5.2 astronomical units. So, you have a region of around 4 astronomical units, which is roughly 4 times the distance between the Sun and the Earth, inside which you can have these asteroids. Okay. So, these are in orbit, they are mainly in orbit over there, and these asteroids, this region is called the main belt. Okay. So, this is called the main belt. So, the asteroids here are called the main belt, are residing in the main belt. Okay. In addition to this, there are various other kinds of asteroids. So, there is a class called the near Earth asteroids, NEA, and these are asteroids whose orbits approach or cut across the orbit of the Earth. Okay. And these asteroids are relatively closer to the Earth, and they are of particular concern to us because we have to be wary about asteroids colliding with the Earth. They could be a big hazard to life on Earth. And it is believed that there have been possibly such collisions in the past, and there are also craters to suggest that there have been such collisions, and if a sufficiently big asteroid falls into the Earth's atmosphere, it will be a catastrophe, much worse than several nuclear explosions going on at the same time. For example, it has been speculated that the dinosaurs going extinct could be related with the impact of a massive asteroid. It has been speculated, it is not well established, but it has been speculated. So, when such an asteroid falls on the Earth, the impact will release a large amount of heat, and consequently there will be a cloud of dust and water vapor surrounding the Earth for many years, and the sunlight will not reach the Earth's surface. This will adversely affect the vegetation and life on Earth. You have clouds over the skies for many years continuously. Okay. So, this will be a tremendous catastrophe, and it could wipe out various life forms on Earth, and after that you could have again new life forms coming through from whatever survives. So, it is possible that there have been such events, and there may be such events in the future also. Okay. So, they are of particular concern to us, and the NASA JPL site, the JPL NASA site has a list of asteroids, and it goes into thousands. Okay. And they also have a list of near Earth asteroids. So, this picture shows you the main belt of asteroids. Okay. The yellow spots over there is the main asteroid belt, and they are in orbit, as you can see, between Mars and Jupiter, and there is this enormous space available to you between Mars and Jupiter, roughly 3 times the radius to Mars. Okay. So, that is available to you between Mars and Jupiter, and you have these asteroids moving around. Now, these asteroids that are in orbit between Mars and Jupiter, this is the main belt of asteroids. They were possibly formed, they were believed to have formed along with the solar system. So, these are small debris of the formation left over from the formation of the solar system. So, they were also formed at roughly the same time, 4.5 billion years ago. But they did not, these objects did not form a planet, and they remained in the form of small objects orbiting between Mars and Jupiter. Okay. So, they were formed along with the solar system when the nebula, the rotating flat disk fragmented, these objects did not form large fragments, they formed say minute fragments. That is a possible explanation for these asteroids, and they are now they have the same angular momentum and they are in orbit around the sun. Now, the asteroids, they include a very interesting class of objects called the Trojans. So, these are also there are Trojan asteroids, okay, and these are objects. So, a Trojan object, let us go in okay, these are, let me tell you what a Trojan asteroid is first. A Trojan asteroid is captured in Jupiter's 4th and 5th Lagrange points. Let me spend a little time discussing this, what we mean by this. Okay. So, we are going to now discuss what we mean by Lagrange points, and it is illustrated in this picture. So, this is something that Lagrange pointed out, the mathematician, a famous mathematician Lagrange. So, you consider two masses in a nearly circular orbit. The planets we know are in nearly circular orbits. So, consider two masses in nearly circular orbits. So, this is the sun, for example, and this could be the Earth or Jupiter. Okay. So, there are two masses in a nearly circular orbit like the sun and Jupiter here, or sun and Earth, fine. Now, we go over to the rotating frame that rotates with the same angular speed as the orbit. The orbits we have seen are near, if it is a nearly circular orbit, there will be one angular speed, it will have an angular speed omega. So, we go over to a frame of reference in which is also rotating with the same angular speed omega. Okay. Now, so we are now in that frame of reference. So, this picture is in the frame of reference which is rotating with the same angular speed as this orbit, and here, so these two objects will remain at the same position under as it rotates. Now, in this frame of reference, let us ask the question, can we place a test particle in such a way in this rotating frame, so that the test particle does not experience any force? Okay. So, in this rotating frame of reference, there are three forces acting on any test particle. The test particle itself does not exert any gravitational force. So, it is a small, it is a low mass particle. Okay. So, we have these two objects, and the question is, can we place a third particle somewhere in this anywhere in this region, in the neighborhood of these 2 points. The third particle is also rotating with the same angular velocity. So, in the rest frame it will have no rotation, in the frame of the orbit it will have no rotation. Can we place this third particle somewhere so that there is no force acting on it? Okay. So, in this rotating frame, the third particle has 3 forces acting. There is a centrifugal force acting outwards from the center of mass, and there is the gravitational attraction of this object, and there is the gravitational attraction of this object. Okay. That is the question addressed by Lagrange. So, in that rotating frames, so can we have a co-rotating object, test particle, co-rotating with the circular orbit, which are there positions where such a test particle will not experience any force? And Lagrange found that there are indeed positions where the centrifugal force and the gravitational attraction of the 2 particles, it cancels out. He did the analysis and he showed that there are actually points where this force cancels out, and these points are called the Lagrange points. Okay. So, if I place a test particle which is, let us say, the Earth Sun system, and I take a test particle that has the same orbital period 1 year as the Earth and place it somewhere, can I find a place? Say I want to place a satellite think of it like this, I would like to place a satellite that has the same orbital period as the Earth around the Sun. Okay, so 365 days. Can I place it somewhere where it does not experience any force due to the Earth or due to the Sun? Okay. And Lagrange found that there are 5 such positions. They are called the 5 Lagrange points and they are referred to as L1, L2, L3. L1, L2 and L3 are collinear with the 2 masses. And L4 and L5 are the 2 other Lagrange points. And L4 is in the leading, so the triangle here L4, these 2 objects, L4 is at the leading, so this point is along the leading part of the motion, this is trailing, okay, L5 is trailing. So L4 is the leading Lagrange point and L5 is trailing. These are off the axis. Now of these 5 Lagrange points, these are all equilibrium positions. So if you have an object placed over here which is doing the same rotating circular motion, same orbital motion as these 2, it will remain where it is under the influence of the force acted by this and acted by this. Okay, but the question then arises, are all of these Lagrange points equilibrium positions? So if I put a particle there and if I disturb it slightly, will it just go drastically away from that position, or will it do some small oscillations around that position? Will it tend to approach back that position? Okay. And if you analyze this problem, it turns out that the 3 Lagrange points that are collinear are unstable. So L1, L2 and L3 are unstable. But there are L4 and L5 which are the 2 other Lagrange points which are not on the axis, and these 2 Lagrange points are stable. Okay. So if I put a test particle in either L4 or L5 and if it rotates along with the Earth Sun system, then it will remain where it is. And it is a stable equilibrium. So if there is a small disturbance, it will just do some small oscillation around that. Okay. So if these are very useful if you want to launch satellites. So for example, take the Earth Moon system. If you want to launch a satellite, it will be good if you can place the satellite in the Lagrange points of the Earth Moon system. Okay. Then there are Trojan satellites. So Jupiter, for example, has many satellites. So if you consider 2 of the Jupiter and 1 of its big satellites as the system, then you can find, it happens that you may find a 3rd satellite located at one of the Lagrange points. Okay, so these are called Trojan satellites. So this concept of this Lagrange point comes in useful if you want to send out satellites around Earth, for example, or satellites in the Earth Sun system, orbiting satellites which will go around the Sun then. Or you can have, you find these Trojan moons, Trojan satellites around planets, and you also have Trojan asteroids. So we have Trojan asteroids, and these Trojan asteroids are in orbit around the Sun at the Lagrange points, at the equilibrium Lagrange points of the Sun and Jupiter. Okay, so you consider the Sun and Jupiter as the 2 objects, and the Lagrange points of this. So this will have some 2 Lagrange points which are stable, and you find asteroids located at these Lagrange points. Okay, these are called the Trojan asteroids. That is a very interesting phenomena. So let me show you where the Trojan asteroids are. See if you can locate them in this picture. Okay, just see if you can locate the Trojan asteroids. So let us look at the picture of the of the Lagrange points. The Lagrange points, you expect them to be over here and over here, right, along the orbit of Jupiter. So let us see where the Trojan asteroids are. There any asteroids along the orbit of Jupiter, right? There are, you will notice that along Jupiter's orbit there are 2 regions where there are asteroids, right? Can you see them? There are 2 regions where you have asteroids along the orbit of Jupiter. One of these regions is over here, and the other region is over here. So, these asteroids lie on Jupiter's orbit. Okay, they do not lie between Mars and Jupiter. They lie on Jupiter's orbit, and they are at the Lagrange point. Okay. So, I will request you to actually go back home and work out where you expect the Lagrange points to be. Where do you expect the Lagrange points to be? Work out where exactly do you expect the Lagrange points to be for this Jupiter Sun system. Okay. So, please take this as an assignment. You work out. You have been given all the parameters that are required in those tables. So, you work out where do you expect to see these Trojan asteroids. Okay. Okay. We also have these centaurs, that is a name given to asteroids that lie beyond Jupiter and that lie between Jupiter and Neptune. So, there are also asteroids that lie between Jupiter and Neptune. They have been given a name centaurs. Okay. And then there are also asteroids which lie beyond Neptune. These are known as trans-Neptunian objects orbiting beyond Neptune. We shall come to this trans-Neptune objects a little later, trans-Neptunian objects a little later. These are objects orbiting beyond Neptune, and some of the big asteroids are also classified as minor planets. Okay, some of the big things in orbit, particularly in the trans-Neptunian region, are classified as minor planets. Okay. So, that is a brief kind of overview of asteroid. Now, next let us go on. The next thing that we are going to discuss are comets. So, what are comets? Okay. So, comets again, these are small bodies, and they are mainly icy. So, they are mainly icy, unlike the asteroids which are made up of rocks and metals, rocky, they are mainly icy. Okay. So, water and dust, so frozen water and dust. There are other elements also in them, okay, which vaporize easily if you heat them. And these are a few kilometers in extent, typically around 1 kilometer, a few kilometers, 1 kilometer in extent. And these objects are believed to have been formed in the outer solar system, where it is cold, because you need them to be formed in the outer parts of the solar system, because you want to form frozen objects, frozen water, you want to have ice and other volatile substances which are in a frozen state. So, you have to form them in the outer parts of the solar system. So, when the solar system was formed, remember, let me just go back to this picture of the formation of the solar system, right. So, you have this disk and this disk fragments. So, in the outer parts you could have had you could possibly have small fragments forming also in the outer parts, and these would contain frozen water and other frozen gaseous volatile substances. Okay. So, they are believed to have been formed in that region, and so they have orbits. So, we believe that they are originally in orbit around the sun, in orbit, and these orbits are disturbed by the massive planets. Okay. So, we know that the planets Jupiter, Saturn, Uranus and Neptune, they are quite massive. So, if you have such icy objects in orbit around the sun, and if the orbit happens to be disturbed by any of these massive planets, then the object will no longer be in orbit around the sun, it will move in some other direction, and some of them may move out of the solar system, some of them may move in, and those that move in will approach the sun, and if they approach the sun within a few astronomical units, then the ice gets vaporized. Okay. So, you have this water vapor and these other volatile substances, they get vaporized and they come out from the, so the core may remain solid. For some of them the core may also melt and the whole comet is gone. For some of them the core remains solid and the outer parts vaporize. So, you have a gaseous outer part and you form an atmosphere around this solid core. Okay. And it is that which is referred to as a coma, and the name comet comes from there. Okay. So, you form an atmosphere once some of the substance vaporizes, you form an atmosphere around a solid core, and the atmosphere could be a few thousand kilometers. Okay, in size. And so this atmosphere is made up of gas and dust, and when it approaches the sun, sunlight gets reflected from this. There are ice pieces, and the whole thing reflects sunlight. So, you see it as a very bright object in the sky when it approaches the sun. Further, the gases in the there are gases in the atmosphere which exhibit fluorescence. So, they absorb some frequency, say ultraviolet frequency from the sun, and ultraviolet frequency that they absorb light from the sun and they re-emit it. So, possibly they could absorb ultraviolet light from the sun, ultraviolet radiation, and re-emit it. Okay. So, this is fluorescence. So, they could absorb radiation from the sun and re-emit it in the visible. Okay. So, which also makes it glow and you have a kind of fuzzy appearance. Okay. And the whole thing also is not, it is not uniformly distributed around. So, if you have a solid core like this, the comet atmosphere does not form uniformly around it, it forms a tail. Okay. It forms a tail in one direction. So, it could be a tail like this. Okay. Forms a large tail in one direction, and the reason why you have the tail points away from the sun, and the reason why it develops a tail, the whole thing does not move together, is because the gas experiences an outward push away from the sun. The sun is emitting out charged particles continuously. This is called the solar wind. So, there is a set of charged particles coming out. The sun is emitting radiation, it also emits out charged particles. Okay, that is called the solar wind. It is a very low density, but it is there. It is a thing, radiation, it is an emission from the sun. And these charged particles coming out from the sun, it is called the solar wind. They impinge upon the gas that is there in the comet, and they make it, they drag it away from the core. Okay. So, as a consequence of this, the gas gets elongated away from the sun. The dust which is there, the dust experiences, the dust which is there in the comets, it is moving towards the sun. Now, the sun sends out radiation, and radiation we know carries energy and momentum both. So, when it is moving in this bath of radiation, it experiences radiation pressure. It is also so it experiences a drag, a force because of the radiation that is coming out from the sun, and that causes it to lag behind the solid core. Okay. So, altogether the dust and the gas, they both form a tail behind the solid core. Okay. So, you see this very spectacular feature which is a comet, and when a very bright comet appears in the sky, it is a really spectacular thing to watch. Okay, you can sometimes even see them in daytime if it is a very bright comet. Okay, so, let me show you a picture of the comet Halley, one of the most famous comets in our history. So, you can see this very spectacular tail in the at the back of the Halley comet. Okay. So, this is the Halley comet. The Halley comet has a 76-year period. So, if you live more than 76 years, you can hope to see it, okay. And you will hope to see, you can hold, you by and large hope to see it only once, I mean you can hope to see it only once in your lifetime. So, I have seen the Halley comet in my third year, 1986, if I remember correctly. Okay. So, those of you who were not born then or who are very young then can hope to see the next time it comes about. Okay. And it was quite a prominent thing in the sky, the Halley comet, comet Halley. And so, the period is not precisely 76 years, there are small disturbances due to the other planets, etc. So, it varies. So, you cannot predict that it will just use this to predict that it will when it will come again, there will maybe a variation within a year. Yeah.
So, when you say that the radiation pressure causes the tail to elongate,
right,
comet because of its atmosphere,
right, right.
Why doesn't it do the same to other planets like the Earth which have atmospheres?
Right. So, the Earth's atmosphere, the dust, it is the dust which experiences the radiation pressure. Okay. Not the, it is the dust and not the gas that experiences the radiation pressure. The gas in the Earth's atmosphere is also moving in the solar wind, right. So, we have something called the magnetosphere around it and the whole thing is distorted because of that, the outer parts, that is the very outer parts of the solar atmosphere. Okay. And the Earth also does not approach as close to the sun as these comets. So, the comets approach pretty close to the sun, well even if it does not, okay. The outer parts of the Earth's atmosphere is distorted because of the solar wind, but that is a very far away.
So, the solar wind interacts?
Right, the solar wind does interact with the Earth's atmosphere. Fortunately, the Earth has a magnetic field which protects it, okay, and protects this, does not allow the solar wind to enter as easily. But there are, the solar wind is there, and when the solar activity increases, you will have more noise for radio signal transmission, okay. So, that is there, that is a fact, the solar wind is there.
So, another question.
Yeah, so one more question.
When you say that you said that the massive planets, there are only 5 Lagrangian points.
Right.
Between the Sun and Jupiter.
Right, right.
Orbit, on which the asteroids can be stable.
Right, there are only 5 Lagrange points,
So,
right.
the other comets which, other asteroids which are between the Mars and Jupiter.
Right.
So, they are also in equilibrium positions.
They are also in equilibrium positions, but they are not in the orbit of some planet.
Yeah, they are not the Lagrange points, but
They are not even in orbits of planets.
yeah, they are between the orbits.
They are between the orbits, whereas these are in the orbit of Jupiter. Okay, yeah, they are in L1, L2 and L3 are unstable. So, small disturbance will move them away. So, they are, you do not find them there, you only find them in L4 and L5.
So, all the thousands of asteroids we have, all are in equilibrium.
They are in stable orbits, right, by and large, yeah, we believe that they are in stable orbits, by and large. I mean, I really cannot say whether all of them are in stable orbits, but they are believed to be in, between Mars and Jupiter, they are in stable orbits.
So, the threat that many of them pose to the Earth, that is when they collide with each other and come up.
No, so there, yeah, so some disturbance could cause them to move, the orbits to change, right. So, there are these near Earth asteroids also, okay. So, there could be disturbances, right, and a disturbance may cause its orbit to change, okay. Right. Before we go, so yeah, this is the, we are discussing the Halley comet, and the Halley comet, it lies in the plane of the, its orbit, no, its orbit is off, okay. Anyway, this shows you its eccentricity, it has a pretty eccentric orbit, eccentricity is 0.97, it is very close to 1, and the semi-major axis is around 17. So, the semi-major axis is actually less than some of the planets, okay. So, let us have a look at what the orbit of the Halley comet looks like. So, this curve over here, I hope you can see it, this curve over here, this is what the orbit of the Halley comet looks like. It just cuts the orbit of Neptune over here in a small region and then comes in. It is inside the orbit of Pluto. Okay. This again is the same thing, but okay, let me go back to this picture. In this picture you can see another orbit that extends in this direction over here, straight out, and that looks like a very eccentric orbit. Okay. So, the same orbit is shown over here, the one that extends out below, and this orbit looks quite different from the one of Halley, and this is the Hale-Bopp comet. The Hale-Bopp comet, I think everyone in this class would have seen it, at least you were old enough to see it. It was seen in 1987, right. It was it was seen in 1997. It was seen in 1997, okay, and it was a very prominent comet. So, that is just 13 years ago, and I think if you had had been interested at that time, you could have seen it. And the Hale-Bopp comet is again, it has a very eccentric orbit, and the orbit is quite different also. The semi-major axis is extremely large. You can see it extends well beyond the planets, and it does not fit into this picture. The entire orbit does not even fit into this picture. It comes here, and then it cuts, and it here like this. So, this is believed to have a time period of 2520 years, something like this, few thousands of years. So, none of us can well, even our in our civilization you might I think the Indian civilization, they would have seen it a few times, or maybe once or twice, but many of the other younger civilizations would not have even been around at that time. Okay. So, anyway, so the comets, so there are roughly have been classified as into two, but there are other types also. We will not go into all the details. There are the short period comets, and these have periods of the order less than 200 years, and these lie roughly in the ecliptic plane or close to the ecliptic plane. Okay. Let us just see where does Halley comets right. This is Halley. Okay. Okay. Oh, sorry. Right. So, these are the short period comets, and you can have comets with periods as short as a few years, and comets with periods as short as few years, they just get wiped out, the whole thing evaporates in a few orbits. Okay. And the short period comets, the time period extends up to 200 years. And you have another class of comets, the long period comets, which have time periods more than 200 years. And the orbits of these generally need not lie in the ecliptic plane. Okay. They are found to be isotropically distributed. So, the orbits could be aligned in any random direction. Okay. And these are the long period comets. And the origin of these comets, where do these comets come from, has been a very interesting question, which has driven a large the solar astronomy, solar astrophysics has been a driving question in solar astrophysics. Where do the comets come from? It is a very important question, very interesting also. You have these objects which have orbits quite different from planets. Okay, where do they come from? Now, there have been various models and various theories proposed. One of the very interesting theories was proposed by this famous astronomer Oort, Dutch astronomer Oort. what he proposed in 1950s, if I remember correctly, no, a little later possibly, sometime in the 20th century, in the later half of the 20th century, what Oort noticed that these long period, he proposed a model for the long period comets. Okay. He Oort observed that the long period comets, they are isotropically distributed, not that the orbits lie in the ecliptic plane, and their aphelion, the furthest distance from the sun, the value of the aphelion for large number of long time period comets, it comes out to be around 50,000 astronomical units, tremendous. Okay. So, he speculated, he proposed that there is a cloud of objects around the solar system, isotropically distributed around the solar system at that distance. So, at a distance of 50,000 astronomical units. Okay. That is much larger than the scales that we have been talking about. We have been talking about tens of astronomical units, and this is 50,000 astronomical units. And this cloud, he proposed, is the source of these comets, the long period comets. Okay. And this cloud is referred to as the Oort cloud. So, what he proposed was that there is such a cloud at this distance, and there are these very frozen icy objects over there, very cold, it is a very cold place, obviously it is very far from the sun, and there are these frozen icy objects hanging around over there orbiting the sun, and then some passing by star. So, in our galaxy there are many stars, some passing star could disturb one of these objects, and if the disturbance is such that its trajectory heads inwards, then it may go into a very eccentric elliptic orbit around the sun. Okay. So, into a very an orbit around the sun, and the orbit would be very eccentric, very elongated eccentric orbit around the sun. So, this was the idea proposed by Oort, and but unfortunately the distance is so large that it is not possible to observe any object at such a small object at that distance. Okay. And there is no observational evidence, direct observational evidence for the existence of such a cloud, such an Oort cloud. Okay. So, the evidence is whatever is there is indirect by just looking at the orbits of the known comets, that is all. Okay. Now, there is another very interesting, yeah, no, we shall discuss that. Okay. So, we shall now consider another class of objects. These are known as the trans-Neptunian objects. Okay. And you may think of them as some kind of asteroids also, these objects. These are small objects, most of them. So, the several scientists have proposed the existence of small objects in the solar system beyond Neptune's orbit. Okay. And this was proposed as a source for the comets, particularly the short period comets or of the comets in general. Okay. It is not that all comets arrive long period, it is not that it is well established 100% that you have the Oort cloud, etc. Okay. So, it is a subject of research, and when you have a subject of research, there are different speculations which are investigated. So, this also was a possibility that was investigated, that you have various objects outside the orbit of Neptune. These are known as trans-Neptunian objects collectively. And suggestions have been made. So, by various people, I just give you three names over here. We have Leonard in 1930, Edgeworth 1945 and Kuiper 1951. And there have been suggestions made after that, before that, etc. Okay, these are just three of the names which I have chosen. Now, currently it is believed that there is a belt of objects, just like you had the main belt of asteroids, you have another belt of small objects called the Kuiper belt, or sometimes called the Edgeworth-Kuiper belt. And this spans the distances 30 to 50 astronomical units from the Sun. Okay. So, the Kuiper belt is a belt, a region of small objects, again coplanar with the ecliptic plane, orbiting the Sun, just like the main belt. It is just like the main belt. The main belt we saw spanned 4 astronomical units, 4 or 5, 4, right, 4 astronomical units. This is a much larger version of that, you may think of it. It spans around 20 astronomical units beyond, and it starts from beyond Neptune. So, these are all trans-Neptunian objects. So, the Kuiper belt or the Edgeworth Kuiper belt is a subset of the trans-Neptunian objects in orbit around the Sun. Okay. And it was proposed as a kind of source for the short period comets. But now it is believed that these are not possibly the sources of short period comets. These objects are stable, are in stable orbit, are believed to be in stable orbit. So, if you disturb them, they will just, the orbits will just get disturbed slightly, and it is believed that there is there is a disk which extends of objects which extends beyond the Kuiper belt, which is referred to as the scattered disk. Okay. And scattered disk objects could possibly be what give rise to these short period comets. So, this there are, I mean, this is the origin of comets, as I have told you, is something which is not very well established, okay, not 100% established. So, you may find other other kind of things given elsewhere. So, it's something which is still not very 100% established. Okay, you should bear this in mind. Now, these proposals were made in as you saw, in 1930, in 1950. After that, people tried looking for such objects, but the distance being so large, 30 astronomical units, it is very hard to detect objects over there. And there was no object found which could possibly be a Kuiper belt object until 1992. The first objects that were part of the Kuiper belt, or the Edgeworth Kuiper belt, these are called EKBO, Edgeworth Kuiper belt objects, or sometimes KBO, Kuiper belt objects. The first such object was discovered in 1992, quite recently, by these two people, Jewitt and Lulu. Right. And what is the method used to find such objects in the sky? What is the method used to find asteroids, for example, okay, or objects in the Kuiper belt? The method is quite simple actually. What you do is, if you take two pictures of the same part of the sky on 2 different days, 2 different nights rather, not on days. If you take the image of the same part of the sky on 2 different nights, then you blink, you just alternately look at these two with your eyes. So, there is a device which actually does that. Okay. It will show you one, then it will show you the other, it will show you one and then show you the other alternately. Now, the stars, they will appear in the same place in these pictures, but the planets or the asteroids, they will move with respect to the stars, right. That is how that is one of the main differences. So, one would be here and one would be slightly shifted, and this slight shifting, if you look at the if you do this thing, if you just bring one picture and then the other and go back to the first one, then your eye will pick out the one that moves slightly, it will just move back and forth, it will blink, okay, and your eye can easily make it out. Okay, so amongst all the objects in the field of view, your eye can pick it up. Okay. So, such things have been done with CCD images, and they can be used to identify asteroids, and that is how this object was discovered. And now at present there are around 1,000 objects known which are members of the Edgeworth-Kuiper belt, and it is believed that there are around 70,000 objects larger than 100 kilometers which are there in the Kuiper belt. Okay. So, it is a tremendous repository of small objects, and these objects, the Kuiper belt, the members of the Kuiper belt are mainly ice. So, they are frozen volatiles. So, frozen ammonia gas, methane or water and water. Okay. So, these are all very, so these outer parts are extremely cold, the temperatures are estimated to be around 50 Kelvin, which is pretty cold, and so you have these objects roaming around in orbit over there, and they are right, and Pluto is a part or now a part of the Kuiper belt. That is quite obvious when you look at the orbit of Pluto. Okay. So, this is the Kuiper belt. Maybe you cannot, here can you, right. So, this region over here outside the orbit of Neptune, you see this yellow thing over here, just outside the orbit of Neptune here, it goes like this. Okay, it is more clearly visible in this picture here. Outside the orbit of Neptune, you have this yellow band over here, that is the Kuiper belt. And you can see that Pluto's orbit, this eccentric thing over here is Pluto's orbit. It is bang in the middle of the Kuiper belt. So, Pluto is a Kuiper belt object. Okay. And Pluto is the largest Kuiper belt object, and it is because of, but not only is Pluto the largest Kuiper belt object, but if you look at the Kuiper belt, you will find that there are other objects comparable to Pluto. Okay. So, let me show you two other objects comparable to Pluto. So, these are called Makemake and Haumea. Haumea actually, it should be Haumea, Haumea, but its spelling is wrong. Okay. So, this picture also shows you Haumea and Makemake. So, this is Haumea over here, and this is Makemake. They are also members of the Kuiper belt, and it should be the name, it should be okay, there is a which should be there in the spelling. So, these three, Pluto, Makemake and Haumea, they are all have all been classified now as dwarf planets. So, I told you about dwarf planets in the last class, and I told you that in addition to Pluto, there is Ceres and Eris, right. We also have two more, they are Makemake and Haumea. These are parts of the Kuiper belt, and they are dwarf planets. So, it is anticipated now that there will be many such objects found in the future which are comparable to Pluto in size. So, it is not meaningful to maintain Pluto as a planet anymore, it is more like a Kuiper belt object. Huh? No, Ceres is, it was classified as a meteor, as an asteroid earlier. So, it is in the main belt, I think, somewhere over there. It is not in the Kuiper belt.
It's beyond Pluto, right?
No, Ceres is not beyond Pluto.
Between Neptune and Pluto.
Yeah, it's before. I think it's inside Neptune. It's not a Neptune object. Ceres.
So
Okay.
all the objects beyond Pluto and within this range.
No, Pluto. All objects beyond Neptune are trans-Neptunian objects. That's a very generic term.
Yeah. And
Okay. Kuiper belt is a specific thing. It's not very not that everybody. It's a subset of the trans-Neptunian object. Okay, and there is still a ambiguity as to what is what. These are just names. Okay, so trans-Neptunian object is a very generic name for everything outside. Now, whether you want to call some of them the Kuiper belt or not is again it's a matter of nomenclature.
Only the icy bodies and calling them Kuiper belt.
Well, icy bodies, most of the things here are icy. Okay. Now, you also have these objects which lie beyond the Kuiper belt. These are the scattered disk, part of the what is called the scattered disk. So, here two of them are shown. One of them is Sedna. This is Sedna, and this is Eris. Okay, and there is one more shown over here. So, these are all beyond the Kuiper belt. This is what is part of the scattered disk. Okay, and these are also quite massive objects. These. So, the exploration of the outer solar system is something that is still an ongoing process. Okay, no satellite, no space mission has still now reached the Kuiper belt. Okay, it has not been studied by a space mission, but there are plans. I think it will be studied in the future. Okay, so this is the frontier of the study of the solar system, and it's a lot of new information coming out about the outer parts of the solar system, and our knowledge of the outer parts keeps on changing now quite I think quite fast. So, let me stop here for today. We shall move on to some other things in the next class.